One of the things we're going to want to do is come up with some broad classification of chemical reactions. It enables us to simplify the recognition of types of reactions. So one of the most easily recognized reactions is this. It's a combustion reaction. The way that we recognize these combustion reactions is that over here on the reactant side, we have O2. The presence of O2 as a reactant automatically classifies a reaction, whatever a reactant is, as a combustion reaction. Now, we may have some other ways of classifying the reactions, but a broad category for this type of reaction with O2 as a reactant is a combustion reaction. Then we have combination reactions. In combination reactions, we have multiple reactants. So in this case, we've got two reactants, but I could have some other reactant here. But the bottom line is all the reactants, however many reactants you have, combine, hence the word combination, to form one product. So that's how we recognize combination reactions, is multiple reactants and a single product. And then we have decomposition reactions. And decompositions are easy to recognize. You have one reactant, and you have multiple products. There could be another product out here, even another product, but the way you recognize a decomposition reaction is that a reactant decomposes into multiple products. So, combustion reactions we recognize because they have O2 as a reactant. We could have different products over here from a combustion reaction. A combination reaction we recognize we have multiple reactants, but we only have one product. If you see one product on the product side, multiple reactants, you know you have a combination reaction. And then a decomposition reaction really just goes the other way. We have one reactant and multiple products. So be able to recognize the different types of broad categories of reactions. So if I were to look at this particular reaction, this is ammonium chloride. And by the way, ammonium chloride is an ionic compound. This is something you have to watch out for. Even though there are no metals over here, remember the ammonium cation is a polyatomic cation. So just think of this as an ion, a cation, and then chloride ion has a negative charge, and they're attracted to each other by this positive negative charge into a crystal structure. So this is an ionic compound, and it is one reactant that's going to decompose into multiple products. So this is a decomposition reaction. Okay, pretty simple. Hopefully that wasn't too confusing for you. Combustion of hydrocarbons and carbon-hydrogen-oxygen compounds. Now, the first thing you want to recognize in this broad category of reaction is that it is a combustion reaction. And if it's a combustion reaction, you know that O2 is going to be one of your reactants. Now, I've mentioned this before. This is a compound composed of carbon and hydrogen. It is a hydrocarbon. Okay? We call this a hydrocarbon. This is actually methane, and methane is the simplest hydrocarbon. It's just carbon and 4 hydrogens. It's combined with O2, so you know that it's a combustion reaction. And whenever you have pure combustion, that is no side products, you have complete combustion of a hydrocarbon, you get 2 products, carbon dioxide, a molecular compound, and water, another molecular compound. So hydrocarbon combustion reactions, as long as it's pure combustion, you get two products, carbon dioxide and water. And the same thing is going to be true for carbon, hydrogen, and oxygen compounds in combustion reactions. They produce carbon dioxide and water. So here's glucose. You are burning this essentially in the process we know of as metabolism. Metabolism, you're combining glucose with oxygen and you're doing this combustion reaction. You're producing carbon dioxide, water, and your other product is a lot of energy. And you're using that energy to do all kinds of things, to do metabolic processes. And there's a lot of waste energy that comes off as heat. So you are, if you're running a normal temperature, you're somewhere in the neighborhood of 37 degrees Celsius. But in any case, that is a carbon, hydrogen, oxygen reaction. That is a combustion reaction. You produce two products, carbon dioxide and water, just like hydrocarbon combustion, which also produces carbon dioxide and water. This is something that I would keep track of. I would remember this. And here we have the good old sun. And the sun is a nuclear factory fusing hydrogen into helium. And ultimately, toward the end of its life, as it becomes a red giant, it will make elements, I suppose, up to around oxygen. That's about, our sun's not that large, so that is, I understand, about the heaviest element it can make. So all the iron and cobalt and nickel and gold and lead, all the heavier elements that we have on Earth came from supernova explosions from many, many billions of years ago that were incorporated into the synthesis of our solar system out of all of that nuclear debris. So in a sense, as Carl Sagan and Neil deGrasse Tyson says, we are made of star stuff. In another way, you could say we're made of nuclear waste. Let's take a look at the mass of compounds. Now, mass is a measure of the amount of material. We talked about that before. It's a property of matter. And there are a couple of terms we need to become familiar with. We need to become familiar with formula weight, which is used to describe the mass of an empirical formula. And all ionic compounds are written as empirical formulas because, as you remember, ionic compounds are crystals, not molecules. So we use the term formula weight, and then we use the term molecular weight to describe the mass of a molecular formula. Let's talk about the mole. And the mole, in one sense, is a furry little beast that lives most of his life underground. His nails, while not very attractive or very good for tunneling under the earth where he lives most of his life. But that's not actually what we're talking about. We're going to talk about the mole in a mathematical sense. And the mole is the amount of matter that contains as many objects, that's atoms, molecules, ions, could be basketballs, marshmallows, hockey pucks, really anything, but it's really only useful for tiny, tiny submicroscopic particles like atoms, molecules, and ions. That is, as many objects as there are the number of atoms in exactly 12 grams of carbon-12, and carbon-12 being our standard for the weights of all, or the masses of all other elements that are on the periodic table. Carbon-12 is the standard. You ought to remember that. And that number is called Avogadro's number, and that number is 6.022 times 10 to the 23rd. And it's just a number of objects. It is the number of objects that is equal to 12 grams, exactly 12 grams of carbon-12, there are 6.022 times 10 to the 23 atoms in exactly 12 grams of carbon-12. But we can use this number to describe atoms, molecules, ions, anything that we want. It's just not very useful for anything other than these tiny, tiny particles. That's Avogadro's number. You need to know it. I'll say it one more time, 6.022 times 10 to the 23rd objects in a mole. Say it with me. 6.022 times 10 to the 23rd objects in 1 mole, which means that if I have 12 grams of carbon-12, I have 6.022 times 10 to the 23rd atoms of carbon-12. So it's a way to weigh something and then use that mass or weight of a substance and determine how many atoms or ions or molecules of that substance that you have. And that's what we're going to do. So let's take a look at some of the masses that are on the periodic table. So let's take nitrogen, for instance. If I look at nitrogen, what it's telling me is that it has a mass of 14.00674. Now, if I'm talking about moles, if I have 1 mole of nitrogen, the element nitrogen, that means that I have 14, and I'm going to go ahead and round this to 2 decimal places, 14.01 grams of nitrogen. So 14.01 grams of nitrogen equals 1 mole of nitrogen. And if I have 1 mole of nitrogen, I have 6.022 times 10 to the 23rd atoms of nitrogen. Okay, let's look at titanium. My glasses frame made out of titanium, a very strong, lightweight metal. It has a mass of 47.867, and I could say grams per mole. So that means if I have 1 mole of titanium, that means I have 6.022 times 10 to the 23rd atoms of titanium. And those 6.022 times 10 to the 23rd atoms of titanium, it means I have 47.87 grams of titanium, and I'm just rounding to 2 decimal places. So 1 mole of titanium equals 6.022 times 10 to the 23rd atoms of titanium, which equals 47.87 grams of titanium. Okay, hopefully you're beginning to understand what the mole means. So let's look at the mole and how big it actually is. It's pretty astounding. So how big is the mole? Well, 1 mole of rice grains is more grains than the number of grains of all grain grown since the beginning of time. If there were a mole of rice grains, all the land area in the whole world would be covered with rice to a depth of about 75 meters. That's a lot of rice. A mole of marshmallows would cover the U.S. to a depth of 600 miles. That's a big marshmallow roast. 600 miles of depth of marshmallows. Because marshmallows, they're, pretty good size. And if you have 6.022 times 10 to the 23rd of them, well, that's how many miles of marshmallows you'd have on the earth. How about a mole of basketballs? Would fit just about perfectly into a ball bag the size of the earth. And my personal favorite, a mole of hockey pucks, would equal about the mass of the moon. So it's kind of like a dozen. We call it the chemist's dozen. Just like 1 dozen equals 12, 1 mole equals 6.022 times 10 to the 23rd. Really only good for tiny stuff. I'll give you a clue about that. If I were to take a little beaker of water or glass of water, I were to put 18 grams of good old H2O. Now, 18 grams, water has a density of about 1 gram per mil. That's going to be about 18 milliliters. That is not going to be much height in your average glass. It's not a lot. That would equal 1 mole of H2O, which would mean I would have 6.022 times 10 to the 23rd molecules of water. Now, let me give you a hint as to just how big a number that is. Let's do this. How many seconds do you think have transpired since the beginning of time? Well, let's see. We can compute that. Most physicists give the universe, I think it's 14.785 billion years. That we think we know to a fair degree of precision. Now, we're just going to convert, and this is billion years. All right, so billion is in the numerator here, so 1 billion years is equal to 10 to the 9th years. Okay, well, 1 year is equal to 365. We got to add that 0.25 days for the leap year. Every 4 years you get an extra day. You get 29 days in February. And then 1 day is equal to 24 hours. And 1 hour, I'm going to go straight to seconds, 3,600 seconds. Okay, let's check our units. Billions of years cancels, years cancels, days cancels, hours cancels. We're going to find out how many seconds there are in, well, since the beginning of time. So let me be dramatic about this. This is X seconds since the beginning, beginning of time. All right, that's what we're figuring out here. To 2 decimal places is 4.67 times 10 to the 17th seconds. So that's 4 point, let me be a little bit neater about it. Well, not much neater. 10 to the 17th seconds since time began. Well, if I have 18 grams of water, I have 6.022 times 10 to the 23rd molecules of water. And I have twice as many atoms of hydrogen as that. That's a pretty astounding comparison. There are more molecules of water in 18 grams of water than there are seconds since the beginning of time. So there he is, Amadeo Avogadro, for whom the number of chemical particles in a mole is named. Smart dude. I don't know how that got in there. Molar mass. Here we go. So the molar mass in grams is numerically equivalent to the molecular mass in AMU. So 1 molecule of water is equal to 18.02 AMU. So if I have just one discrete unit of good old H2O, 2 parts hydrogen, 1 part oxygen, just one of these, okay, kind of looks like this. It weighs 18.02 AMU. Now here's the cool thing about the mole. If I have a mole of water, that means I have 18.02 grams of the stuff. So if I multiply this one molecule by 6.02 times 22 times 10 to the 23rd, I have 18.02 grams. So that's how I got 1 mole of water is equal to 18 grams. Don't round off to whole numbers, at least 2 decimal places in all your calculations, please. So the numerical mass of H2O is equal to the mass of 1 oxygen and the mass of 2 hydrogens, whether or not you're talking about a molecule in AMU, atoms in a molecule, or a mole in grams. Same number, okay? Different unit. The molecular mass, 1 molecule, 18.02 AMU. This is oxygen. Oxygen is 16 AMU per atom. Hydrogen, this is hydrogen, and hydrogen is 1.01 AMU per atom. I have to multiply it by 2 because the formula for water is H2O. And so that gives us 18.02 AMU. If I have 1 mole, I'm going to have the same ratio. The only difference is the unit, which is grams. And this means that I have 1 mole of the stuff if I'm in grams. So if you're talking about molecules, you're weighing in AMU. If you're talking about moles, you're weighing in grams. And that's what we're going to use most of the time.